also you can look at again at the YouTube. Okay, so this is organic chemistry mechanism. Here I'm going to solve the first two problems. So let's read the problem here first. Consider the compound below and predict whether the leaving group will favor SN1 or SN2. So this is a you have to recognize this is a leaving group. This leaving group is it good or is this a poor leaving group? This is a good leaving group. Because what the leaving group does is they are going to take these two electrons in the bond and then carrying on to themselves. So by doing so, what they're going to generate is H2O, which is a neutral. So therefore, this is a good leaving group. The good leaving group means this one can be a favorable process. So once you generate this good leaving group, you ended up making carbocation. So this is therefore this is a unimolecular reaction, and that has been the whether it's SN1 and SN2, SN1. So this is a unimolecular reaction, generate a carbocation. Later, because it's an SN1 reaction, the second step is now the nucleophile is going to go and trying to make a bonding, right, with a carbocation. So the answer is SN1. So number two is actually quite tricky problem, and is a pretty difficult problem actually to solve. It is the clue is they say this is an elimination reaction. Elimination reaction. What is a product? We know that the product will be an alkene. So that's something that you want to know. And then how does it go is elimination means this RO minus we call alkoxide you should see as a base, because that's the region, and this alkoxide is actually strong base. So therefore this one will be a E2 mechanism that the base is actually trigger the reaction. So they are looking for base is looking for something that is H plus, right? They are looking for something that trying to take it. And where do they going to take is the hydrogen over here. Okay, so this lone pair electron is going to take the hydrogen, and then they're going to make the double bond, and the chlorine will be a leaving group. So that's the reaction mechanism that you guys can see. So why this problem is a little bit tricky now is if you're looking at, however, now you'll be looking at the three-dimensional conformation. What you can see here is you are going to do the Newman projection. So Newman projection is circle is in the back and the dot is in the center, and then now you see, okay, I can see this this one being the if I look from this side, okay, Newman projection. If I do the Newman projection from this side, what I can see here is in the front one, I can see the methyl sticking out, and hydrogen is there, and then the ethyl, right? So CH2, CH3. So this is what from front. So if I do this as a circle, that's the one, and then what's in the bag is this one, and this one is, if I recircle it, that's the one in the back. I can put it in a bigger circle, but put it in the same color in the back carbon, and then what you see here is this is in the same plane, right? This is the same plane as the ethyl, so that's in opposite. So that will be a methyl. And then if this is a methyl, then chlorine is on this side, and then hydrogen on the other side. And then, as you anticipate, this hydrogen, and that's the chlorine. Right? So what according to this notation, what's going to happen is, okay, so base can go and take this hydrogen, and essentially chlorine will leave as a leaving group, leaving the double bond behind. Right? So this portion is essentially formation of the double bond by having this E2 mechanism because you have a strong alkoxide base. But having considered that, if you start to notice, wait a minute, this is quite crowded, right? So we are asking the base coming to this side and chlorine to this leaving to the other side. This is not geometrically very crowded. So this concept about steric hindrance come into a play here, and then we start to, the answer key actually shows in the following diagram, which is the same thing. You have a hydrogen here and chlorine here, and that's the same notation as I shown up there. Okay, can you guys see that? The one in the center is in the front is showing as a dot, and the one in the bigger circle, that's the one in the back, and then you should see that they're the same. And what this is about is, now I can start to draw. Okay, this is the one, and this is a carbon, and this is a carbon, and then you have a hydrogen, methyl, and ethyl. And the one in the back is essentially methyl, hydrogen, and chlorine. The idea here, once more, is they are on the same side, and having the base coming in on to this way, and this one is a leaving group, is quite crowded. So now, therefore, having this idea, say, okay, this is a rotation around sigma bond. That's always possible. Right? Think about, you rotate those, and then until you make this one to the opposite side. Right? So what do they do is actually they look focusing on the hydrogen, and then when you rotate this way, rotate the other way, finally they put the hydrogen that is ready to be extracted by the base on the opposite side. So if you look at now, after the rotation, hydrogen on here, if you see that the methyl and ethyl that used to be here is now goes over here. And then now I think that they are keeping the methyl, hydrogen, chlorine the same as they are before. So this one doesn't change as they are. We just need to rotate them, and for the one, doing this way, so that now you have this rotation. So it is now there is a little notation here. It says anti, and the anti is because of the now alkoxide, which is the base. Now this one likes to go and take the hydrogen away from here, and then make this one a good leaving group, and you are forming the double bond in between the front carbon and the back carbon. Okay? And then based on this, now we can start to write it as, okay, so this is a front carbon, so there's a double bond, but it looks like an ethyl and a methyl on the same side, right? and then this one is here is methyl on this here. So this is like CH3, and the CH is 3, and that's an H, that's an ethyl, right? So that's what the compound is about. So this is a final product of this. If you are looking at here, saying if you do not do the rotation, sigma bond rotation, if you don't do that, if you just without considering this, okay, base coming in and this one is leaving there, and you will see that that's the front and this is the back, so you form the double bond, and then what do you see here is methyl and the methyl are on the same side, right? So this is a front carbon methyl, and that's a back carbon methyl, and then this one is an ethyl, and this is an hydrogen, right? I put a dotted one because you didn't correct for the geometry for the steric hindrance. So this is the wrong answer, and this is a correct answer. Okay. And so they're supposed to be this way. And in the nomenclature-wise, this is I kind of spend quite elaborate this way. For the cis and trans nomenclature, this is we are just counting the one. This is one of the tricky one. This is a cis. This is a trans. Whereas this, oh, I'm sorry, I'm still get confused. So they are on the same side, and we are looking at the same group. So this is a cis, and this is a one that on the base on the double bond, they are on the opposite side. So this is a trans. So trans is a correct product on this. And also, Dr. Ma mentioned this. Also, organic chemistry is quite widely used for the nomenclature. This is a E2 versus Z nomenclature, and then this is a high priority, and this is a high priority on the opposite side of the double bond. So this is on opposite. Right? Opposite means an Eintkagen. So this is an E isomer. Whereas this one, you have if you look at this, this is a high priority, that's a high priority, and that's a Zuzamen. So this is a Z is an isomer. So this is one of the rare cases actually Zuzamen together, isomer is on the trans isomers. At any rate, this is a one that you want to configure the concept about Newman projections, and then its rotation around the sigma bonding is possible. But I think the more this is a very detailed. To me, the most important concept is actually trying to recognize this one. This is an alkoxide. Well, okay, that's a strong base, so it should be an E2 mechanism. I think that you should see that when the base is strong, where your alkyl halide compound is not so reactive, still they are going to be aggressive enough to take any protic hydrogen away at the expenses of generating the double bond. And that is how many people are generating the double bond in the compound using the alkyl halide. Okay. So if you have any questions, let me know. But I have a very short summaries here, and to try to give you another overviews on what's going on here. So here is I wanted to give you a summary for the organic chemistry portion number 2, and let's just focusing on. I'm going to ask you. Okay, I'm considering doing the SN1 or SN2 mechanism. And which one will be the faster in terms of SN1? Can anyone tell me which one will be the faster? A versus B. You guys can tell me that. Well, I don't know, or you can say A or B. So I'm just talking about SN1. SN1, which one is the fastest? What, can you see my hands? Yep. Are you guys there? Can you listen to me? Well, should I just didn't talk about? Okay, nobody's responding then. I think that I'm going to stop my lectures. Okay. Okay, did you hear my lecture so far? Oh, you're listening. Okay, thank you. Oh, you're listening. So I'm just giving you the questions about, if you see here, the question is about SN1 reaction, and then this is a two compounds, and this is both an alkyl halide. And so I guess we are talking about same leaving groups here, right? But which one will be preferred to the, if I were to putting this one for the same nucleophile, which one will react faster? And I'm talking about SN1. The reason is, and you should think about, the answer is this is a faster SN1. The reason is because once the leaving group iodide is left, we are thinking about writing this, right? And then this one is, what about that? You are going to end up having this once the iodine group left. For the SN1 reaction, you have an iodine group live, right? So this one is iodine group left. So therefore, which one is more stable? This is more stable. So therefore, faster for SN1. So does it make sense to you? Wow. Okay. Thank you. Thank you for those who have send a text to me. That means a lot to me. Okay. So I'm not. It looks like I'm talking to a wall in the morning. You guys are probably tired, but I'm tired as well. And I think that not because it's in the morning, because I want to have your more questions or the response. It's much difficult to carry out, but I think that you are in the same boat with me too. So this is a one. Okay, so let me change the colors around. Let me use let me choose a purple. So what about the SN2? SN2 is we are essentially we need to have a nucleophile, right? Looking for and to react here, right? So this is a strong nucleophile, and trying to react with this because that's the one partially positive, right? Because of the iodine is the electronegative group, so they are pulling the electrons out. But if you have a strong nucleophile, and this is a case, and which one will have a faster SN2 reaction? Methyl iodide or the tertiary butyl iodide? So that's the one, right? So here's a tricky part. That's why the answer is obviously I think this is a faster SN2. And why it will be that, right? Think about why it will be that. And if I draw the carbon here, and then this is an iodine, and you have methyl groups, so it's a hydrogen, right? And as you remember, I talked about the inversion mechanism, that nucleophile comes from the other side and trying to make a connection here and pushing this other thing outside. This is an SN2. Can you see that picture clearly, right? And then now I'm drawing this the same thing, carbon. So carbon is attached to the iodine, but this time we are talking about this. Methyl, methyl, methyl. And then same thing as a nucleophile, which is strong nucleophile, trying to make a bonding here. Right? So this is an SN2 reaction. And for that, how I'm going to put these colors right? This one is big, right? So therefore, to have an access to the carbon in the middle, there is what is called a steric hindrance. So that's why steric hindrance make it slow reaction. Reaction is slow. Right? Well, whereas here, if you look at the other side, it's just a small hydrogen, right? So therefore, this one can have an easier way to go in. Right? So it's all about the steric hindrance. So therefore, faster for SN2 when you have just a simple CH3I is there. Right? So therefore, the fastest, the answer for all the things that we said, SN1, B is the fastest. SN2, A is the fastest. Okay, so that's the one. That must be another way to looking at the same problems, and I'm here giving you the question. Here I made this table once more. So before I go, actually, let me talk about this too, right? So which one will be fastest for A and B? It is the same idea. Oh no, I think that let me just stop there. So I want to go here to this is a important table that I wanted to kind of finish that one with you. Okay, so I said here as a lone pair types of electron. So compound that contains a lone pair. So nucleophile. That's why we call nucleophile with these two dots. The base with the two dots. So those are the one looking for something that is positive carbon. Okay, so this one looking for carbon with positive carbon and trying to make a bonding with that carbon, right? And this is the one is essentially hydrogen, right? This is in a way you want to call it a delta plus because electrons are being stripped away, and then that's the one is trying to make a bonding with a hydrogen over there. But what about if you have a strong nucleophile, weak nucleophile? So by the definition of when you say nucleophile, we are talking about nucleophilic substitution reaction, right? So the types of reaction is nucleophilic substitution reaction. And the keywords that you're looking for is, okay, if I have a strong nucleophile, it doesn't matter that what's going to happen. I am just go ahead and trigger the reaction. So the nucleophile is part of the reaction. And this is a SN2 types of reaction. But when you have a weak nucleophile and you need to wait for things, essentially leaving group leave and then generate a carbocation. So therefore, it is the rate determining step is, for example, the Rx becomes a R plus and the Cl minus. So that's the rate determining step, and then this is essentially a single molecular step generating the carbocation. And there, you remember that there is a lot of problem that we're trying to cover that. This one, when you make the carbocation, there's a carbocation rearrangement is possible. So that is an idea. So when you have a weak and you just wait, right? Things are dissociate by itself, and the nucleophile make the bond. Whereas when you have a strong nucleophile, essentially this one is a push and pull and push mechanism, as I showed before, right here, right? This goes in and they live together. It is sort of the two molecular mechanism they are doing together, right? Whereas an SN1, as I mentioned before, we are talking about just generating the carbocations, and we want to compare the stabilities. So the rate kinetics, I think that Dr. Ma has many slides. I'm pretty sure he talked about it there. And here you are going to say, okay, reaction rate K times, we call Rx times nucleophile. And whereas the rate here is a K times just Rx. The concentration nucleophile is not part of the rate determining step. Once again, this Rx is alkyl halide. Alkyl halide. Such as a CH3, CH2 minus the bonded with an iodine, for example. Okay, so that's an example of alkyl halide, and the nucleophile is those. Okay, so let me have a fresh new start for the base one. So let me try to use a different category. So let me use a purple color. So base is essentially they are looking for they are looking for the hydrogen, right? This hydrogen, they're taking it, and then neighboring hydrogen, you're forming the double bond here, and the leaving group Lg will leave away. So as a result, you're forming the carbon-carbon double bond. So that's what you have keep you in mind. The fact that we are saying that, okay, we are going to categorize a base, that means already is an elimination reaction. Okay? And when the elimination, if you have a strong base, right, is already whether the alkyl halide, the leaving group is a good leaving group or a poor leaving group, it doesn't matter. It's just going to kick it and then take the leaving group out. Okay, they're going to take the hydrogen out, and leaving group will be kicked out, and the double bond will be formed. So it is a bimolecular collision. So same reason they call it is an E2. So there's a consistency here. Strong nucleophile means a bimolecular SN2 reaction. Strong base means bimolecular elimination reaction to generate the double bond. And so does a weak base is an E1. Right? So the same reason that you can think about, okay, so this one is Rx times B. Okay? And that's an R times Rx. So those are the reaction mechanism that I added on from I think the last time I talked about here. So you start to develop this clear concept about the stability of carbocations and monomolecule, bimolecular natures. And here I think it probably once more steric hindrance. Steric hindrance is a bad for the bimolecular reaction because this is not crowded, whereas the second one here is more crowded, right? So therefore, this is faster for the SN2 reaction for the one with the less steric hindrances. My final thing about this is probably it has been emphasized about carbocation, tertiary carbocation, and probably you will know it by now. Sometimes they are making this arrangement, right? So this is a carbocation arrangement by hydride shift or methyl shift, and you have carbocation rearrangement. So this is something that we've been talking about. Well, that will be a good one, right? They're trying to make that happen, trying to make the one. But this is not only the stable carbocations. If you're looking at something looks like benzene group with a CH2 or C with something over there, I'll just leave it out just like that. And this is what we call the benzyl group. benzyl carbocation. This is actually very, very good, very strong carbocation. So if they can make this a benzyl carbocation, they will want to do it as well. Okay, so that's one of the one, and the other one is actually looking at this. This is on what they call allyl carbocations. Okay, so when you start to talk about this, and this is getting into the more depth knowledges. So this is all the stable carbocations, not just tertiary, looking for something like a benzyl carbocation and the allyl carbocation. The reason is because this one has you are seeing the pi bonding here, and then they essentially have a resonance stabilization. So this positive charges is actually kind of distributed around the ring, and that's why the benzyl carbocation is a stable form. Okay, and I think